So today we'll talk about vertical asymptotes, infinite limits, and we already discussed this a little bit, but where limit does not exist. So let's start with that topic. We had discussed that limit as x approaches a of f of x is equal to L if and only if the left-hand limit as x approaches a from the left, is equal to the limit as x approaches a from the right. Now, we showed one piecewise function as an example, but how can a limit fail? Can I show you an example where the limit still fails for a regular function? And it turns out there is. So, and there are several examples like this. This is just a prototypical one that you should think about. What's the limit as x approaches 0 of sine of pi over x? So let's do some sanity check. If we actually plug in some values, so here f of x equals sine of pi over x. If I plug in values on both the left and right hand side of 0, what do I get? So f of 1 is just sine of pi, which, friends, is just 0 from your unit circle knowledge. Now let's plot a couple of points. Let's keep going closer between 1 and 0. What happens when we plug a half? Well, that is sine dividing by a fraction. It's the same thing as multiplying by the reciprocal. Sine of 2 pi, which is 0. F of 1/3 is sine 3 pi, still 0. We can keep doing this forever. Let's do f of 0.01, that is sine of pi over 0.01, which is actually sine of 100 pi, which is equal to 0. Now, going from the right, it seems that we're going to 0, but that is where things fail. If we actually graph the function and plot more points in, this is what we see will happen. Function looks something like this. It's really nice till -1. Then it does this thing. And at 1 it goes back. This is definitely not drawn to scale, but and there's like 100 turns here, a billion turns here. I'm just summarizing. So it does hit 0 at some points, but the left and right hand limits never equal the same thing. They always bounce up and down and up and down and up and down. And that's why we say that the limit does not exist. Okay, so that's one way. Now we can also have vertical asymptote and infinite limits. So let's look at that example. Find the limit as x approaches 0 of 1 over x squared. Okay. And if we graph it, what we'll get is this behavior. On the left-hand side, get something like this. On the right-hand side, we'll get something like this. And one good way to visualize this is also graphic. It's also by a table. So if we get x and our y, or f of x, right? If I plug in -2, I'll get 1 over 4. If I plug in -1, I'll get 1. If I plug in +2, I'll still get a 1 over 4. +1, I'll still get 1. So basically it's a reflection. And if we plot smaller and smaller values, if I plug in, let's say, +1/2, That's 1 over 1/4, which is 4. And I'll get the same thing on the negative side as well. So it's getting closer and closer to which value? As x goes to 0, on the left-hand side, we're getting closer and closer, and on the right-hand side, we're getting closer and closer. Both times, we're getting closer to infinity. So we have infinity as the answer. And what we basically have shown here is there exists a vertical asymptote, or we know because it's undefined at x equals 0, we have a vertical asymptote at x equals 0. Now, is it always the case when we have vertical asymptote that we'll get infinity as our limit? And the answer is no. And this is the final edge case that I'm going to draw for you. If we have some behavior like this, you get a vertical asymptote, and it can be at x equals any value. I'm just showing at 0 for comparison. If your function does something like this, it goes to infinity at one point, but on the other half it goes to negative infinity. Now, limit as x approaches 0 from the left is negative infinity, and limit as x approaches 0 from the right is positive infinity. And since left hand limit is not equal to right hand limit, the limit at x equals 0 does not exist. Anyway, that's all we have for today. See you next time.